Alright, this is Geometry, Chapter 2, Section 1 and 2, Inductive Reasoning and Deductive Reasoning. So, this is going to be our introduction into proofs. We'll start proofs very, very soon. But before we get there, we have to talk about certain types of thinking a lot in terms of logic. The first one they talked about is that of inductive reasoning. Inductive reasoning. And for something to be considered inductive reasoning, it's a situation where you make a logical argument or a logical statement based off of patterns that you observe. Based off of patterns you observe. That is inductive reasoning. Inductive reasoning. So, an example of that here is if we look here at the bottom, it says 45, 40, 35, 30. What's the next two terms? Well, if you notice the pattern, it's being subtracted by 5, 45 to 40. $45 to 40, right? We're losing 5. 40 to 35, we're losing 5. 35 to 30, we're losing 5. So the next two patterns is probably going to be 25 and 20, just assuming that we're still minusing the 5, minusing the 5. This is an example of inductive reasoning. We see a pattern and we can make a statement, a logical statement, or some type of guess or some type of inference based off of the pattern that we see. The next picture, or pattern rather, we have this rectangle. And then this rectangle has like another quadrilateral in it that has its corners hit at every piece like that. And then in that, it has a piece like this. Again, they want to know the next two patterns. So this is the pattern that we see. So just looking at the pattern, it's probably safe to assume that it's going to do the same thing again. And it's probably safe to assume that it's going to do this again based off of the pattern. We were able to make a inference, an educated guess off of the pattern. So these are the next two, red and blue, inside, and that's probably going to be the pattern of the next two patterns of this particular figure, just based off of the picture. So the conjecture I think of a conjecture as an educated guess. It's not necessarily. It's a little bit more involved in an educated guess, but I think of it as an educated guess. The book says it's a conclusion. Based off of your inductive reasoning. So we look at the pattern and we can make some type of conclusion or educated guess. Okay. So they give us another pattern, R, W, B, R, W, B. And they want to know what you can make in terms of the 21st term. So this is the first, second, third, first, or fourth, fifth, and sixth, right? So we have the same R at the fourth. We have the same first and fourth. We have the same W at the third and fifth, and then the same B at the fifth and sixth. So it looks like it's adding every 3 to get to the R. So 1 plus 3 is 4. 2 plus 3 is 5. 3 plus 3 is 6 for the B's. So if we want to talk about the 21st term, we just keep adding 3 until we get to the 21st term, and then we can make a conjecture of what that pattern might be. So I'm just starting with R. So we're talking about 1, 4, 7, 10, 13, 16, 19, and 22. That's that. So if the 22nd term is R, what's the number, the letter right before R? It's B. So it might be safe to assume that it's B. So let me look at 3. So we have 3, 6, 9, let's see where I'm going with it. 12, 15, 18. Hey, look at that, 21. So since these are all the next terms that's going to be B, it's probably safe to assume that the 21st term is going to be B. And that's just making an educated guess off of the pattern. Just making a conjecture. What do I observe from the pattern? So this one says, what conjecture can I make about the sum of the first 30 even numbers? So I'm going to go through the example. So here's the first term. So we have things in terms of terms. All right, we have our first term. Our first term is the first even number. This is the sum. The first even number that we see. So the first term would be 2. We can think of this as the first term times the sum, because it starts off at 2. There's nothing to add it with. So we think of it as the first term, which is 1, times 2, and that's going to give me 2. Then we have the second term. The second term, remember, we're adding even numbers. So 2, 4, 6, 8, 10. We're adding 2 plus 4, and that equals 6. We can think of 6. We can think of 6 as the second term times the number 3. Then we have the third term. 2 plus 4 plus 6. That equals 12. we can think of that as the third term times 4. Notice it's 2, 3, 4. 1 times 2, 2 times 3, 3 times 4. So it's always the first. So we have on the left hand side. So look at the multiplication, right? Just looking at the pattern. We have 1, 2, 3, 4. If we look on the right at the right hand side of multiplication, we have 2, 3, 4, 5. So it looks like it's on the right hand side one more than on the left hand side. So if we look at the fourth term, this is 2 plus 4 plus 6 plus 8. So that's going to be 20. So that's 4 times 5. So it looks like if we call the numbers on the right hand side n, it's being multiplied by n minus 1 on the left hand side. So if it was 2, it's going to be multiplied by 1. So if I was to say where n equals the term, so if I was to say the 30th term, actually, these are the terms over here. It will be n times n plus 1. Now that I think about it, where the n is the number of terms. So if it was the 30th term here, it would be 30th times the 31st term. 30th term plus 1. And that would give me some number, 930. So I would say that the 30th term is 930 by looking at this pattern. So it says, what can you make about the first odd numbers? So let's take a look at that. The first odd numbers. So it would be 1. All right. This one would be 3. No. 1 plus 3. So it would be 1 plus 3 plus 5. So it would be 1 plus 3 plus 5 plus 7. Alright. So this would be 1 times 1. This would equal 4. So this would be 2 times 2. See the pattern? This would be 4 plus 5 is 9. That would be 3 times 3. And then this is 4, 9 plus is 16. And oops. That would be 4 times 4. And the reason why I get this number is I'm starting this with the n term. So it looks like for this pattern, if the term equals n, it's going to be n times n, or you could think of it as n squared. So then this would be 30 squared, which is 900. Right. I think it would be 900. 0, 0, 0, 0, 30. Yeah, 900. Would you look at that? Cool. So we can also make conjectures or educated guess off of guesses. So these are the months: November, December, January, February, March, April, and May. And they're saying, well, what inference can I make from June And it seems to be dropping every 500 or so, approximately. Sales are going down. That's not a good trend. So, what conjecture? I can make a reasonable guess. Is the reasonable guess that it looks like, based off the graph, it is dropping 500 bucks approximately every month. So, what can I say? I can say this bad boy will probably be, since May is 8,500, then I can say June will probably be 8,000, since it's dropping every 5. Again, based off of the example. We also have a counter example. In a counter example, a counterexample is a situation where if I have a statement and I make a conjecture out of that statement, the conclusion, the counterexample is a the counterexample is an example that proves the statement false. Counterexample is an example that proves the statement false. Statement can be also conjecture, since we're using the right terminology. That proves the conjecture false. So, we have examples of conjectures that we can prove false with a counterexample. This one says if a flower is red, then it's a rose. If a flower is red, then it's a rose. Can I think of a flower that can be red and that's not a rose? Carnation. That's a flower that's red and not a rose. So this would be my counterexample to that. That statement, I just made it false. The conclusion false. This is the conclusion right here. It's a rose if it's red. So that would be my counterexample. Okay. Another one. So this would be carnation, or anything that's red that's not a rose, which is a lot of stuff. If you know your flowers, which I don't, by the way. One and only one plane exists through any 3 points. So, it says through any 3 points. Remember that we need 3. So, one and only one plane exists through any 3 points. So it says through any 3 points, right? What about collinear points? We said that if we have 3 collinear points, this can't be a plane. They had to be non-collinear. So we just proved a counter argument, because that is a set of 3 points that is not a plane. Therefore, it can't just be any 3 points. It has to be non-collinear. Okay. When you multiply a number by 3, the product is divisible by 6. When you multiply a number by 3, it is divisible. The product is divisible by 6. Okay, well, what about if I multiply that number, or the number that I multiply is 1? 1 times 3 equals 3, and 3 is not divisible by 6. If I get 3 divided by 6, I get 1/2. I don't get a whole number. Therefore, that's my counter argument. My counter example. 3 times 1. Alright, so that's that section. Look at patterns. Based off the patterns, can you make an argument? Or not, a conjecture or not. And if you like a conjecture, can you make a counter example? Alright, this is the crux of proofs, the beginning of the different world of proofs. Section 2, that 2. Here we have conditional statements, if-then statements, hypothesis, conclusion. So, this is the world of what we call deductive reasoning. And deductive reasoning is using evidence whether it be postulates, theorems. We'll get to what those guys are in a minute. And rules to come to a logical conclusion. Using evidence, postulates, theorems, and rules to come to a logical conclusion. Okay? The main tool that we use in deductive reasoning is something called a conditional statement. A conditional statement. Oh, goodness. And a conditional statement is a hypothesis and conclusion, usually in the form of if and then. If I do something, then something will happen. It's an if-then statement. And the if-then statement actually has symbols. The if-then actually has statements, and it's in the form of this symbols. And the symbol for this if-then statement is P then Q. This means if P then Q. This is the symbol, and the symbol means that if P then Q. So let's talk a little bit more about what the P means, and let's talk a little bit more about what the Q means. So when we talk about conditionals and P's and Q's and the little arrow, P means hypothesis. P is your hypothesis, and P is always after if. Anything after your if statement is your P. Whoops. Okay. Q is your conclusion. And your conclusion is always after then. So when we put this together, it's going to be if P then Q. If P then Q. Okay? That is a conditional statement. We have a hypothesis P, we have a conclusion Q, and it's in the form of if something happens, or if this scenario occurs, then this thing will happen. If this scenario occurs, then this thing will happen. We also have something called the negation. Which also has a symbol. And the symbol for negation is this little squiggly, and that essentially means not. So if I have my hypothesis P, I can have the little squiggle, and I can say this thing, and that means not P. So it's almost, you can almost think of it as a negative, the negative of P. We can think of this as not Q. So the negation is basically the opposite. So if P was if I drove to the car, if I drove in a car, then not P would be if I didn't drive in a car. Or if I walked, the negation would be if I didn't walk. Or if I fall, the negation would be if I didn't fall. And it also, the negation could be an opposite of a negative too. So if my initial statement, my initial hypothesis was if I didn't walk, then the negation that would be if I did walk. So it's always going to be the opposite of the part of the statement that we say. It's the opposite statement. So we could think of this as opposite statement. It's an opposite statement. So they give us a bunch of stuff here, a bunch of concepts. The first one they give us is the conditional, which we had first. And that's if P then Q. P then Q. This arrow means the if then. So if P then Q. Okay? That's the symbol. And an example they have of this is, here's the example. If angle A is equal to 15, then angle A is acute. That is my example. If angle A is equal to 15, then angle A is acute. And we'll talk about the truth values of these guys in a second. Actually, no, we can talk about it now. This is true, right? If I have something that's 15, then I know that it's acute, so I give it a truth value. And the truth value is basically saying, is it true or false? So I'm going to write T for true. That is true, because 15 is less than 90 degrees. What if I had another statement, and we're going to call this statement the converse. Kiss my converse. All right, and the converse, the symbol for that is if Q, then P. So I switched it. My conclusion is now in front after the if, and my hypothesis is at the end after then. So when I write this out, this is going to be if this was my first initial. A is acute. So if angle A is acute, then angle A equals 15 degrees. When we talk about a true or false conditional, so a converse is a conditional. A converse is a conditional where the Q and the P switches. If I want to prove a conditional false, I have to pick a scenario where the hypothesis is true. The hypothesis is true, but the conclusion is false. So can I think of a situation where this hypothesis is true and the conclusion is false? I have an acute angle, but the angle doesn't equal 15. I have an acute angle, but the angle doesn't equal 15. What about 10? What about 1? What about 4? What about 89? Those are all situations where the angle is acute, but the angle is not 15. Therefore, this guy is false. I can think of a counterexample for this conditional. This is not true. And I can think of a counterexample. Then we have the inverse. And the inverse means not Q, then not, not P, then not Q. Not P, then not Q. So what did I do? Here's my initial statement, P and Q, and I just put the negation symbol, the negative of it. Negative P, negative Q. If not P, then not Q. So the initial statement is if A is equal to 15. So we can say if A is not equal to 15, we'll do this with the equals on. Oops, if angle A is not equal to 15, then A doesn't equal then angle A doesn't equal or angle A is not acute. Angle A is not acute. This guy is also false. And remember, I can think of something that proves the hypothesis true, but the conclusion has to be false. So, again, angle 10, right? Angle 10 is not, oh, I'm sorry. I can think of an angle 100. 100 is not 15, right? That proves the hypothesis true, but it's also, I'm sorry, not acute. 10. 10 is not 15, and 10 is acute. So this proves this guy false. 10 is not 15, so this guy is true. But 10 is also acute, but this says that A can't be acute if it's not 15. So this is saying only 15 can be acute. That's not true. So I picked the inverse, counter example of that inverse. Then we have something called the contrapositive. One of my favorite words to say in geometry. Contrapositive. So contrapositive means not Q, then not P. Not Q, then not P. Okay? So if we do that, for this one, we would say if A is not 15, then angle A is sorry, I made it. So contrapositive is two things. My fault. Contrapositive is the negation of it, and contrapositive is a converse put together. So I'm switching the P and the Q's, and I'm doing the negative symbol. So this is going to be if if angle A is not acute, then angle A doesn't equal 15. There we go. If angle is not acute, then angle A doesn't equal 15. So I have to remember, think of something that makes the hypothesis true, but the conclusion false for something to be proven false. And I can't think of a situation where A is not acute and A doesn't equal 15. So what's not acute? 100, 180. Well, 180 and 100 is not 15. I can't use like 10 or 50 because 10 or 50 are acute. That would prove the hypothesis false. Remember, this has to still be true, and this has to be false. So this makes it a true statement. So a couple things to note. Notice that the conditional. So let's all this condition number 1 and condition number 4. This is 3. This is 2. Notice that condition number 1, the conditional, and the contrapositive are both true. When you have a situation where you have statements where they're true, those guys are called equivalent statements. The contrapositive and the conditional are the same statement. They're just written differently. The converse and the inverse here are also the same statement because I can use the same example to prove these two guys false. I can't prove these guys false, so these guys are equivalent statements. Why do I know they're equivalent? Because they say they have the same truth value. They're both true and they're both false. So these guys are equivalent statements. So when we talk about equivalent statements, those are statements with the same truth value. Statements with the same truth value. Okay. So they want us to write the converse, inverse, contrapositive of the conditional statement true below. What's the blah, 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 blah. All right, so here's the first one, the conditional for this statement. So this would be conditional. Actually, I'll write it as it's simple. Here's my conditional, if P then Q, and my statement is if a vegetable is a carrot, then it contains beta carotene. I'm going to use has to save space. It has beta carotene. I'm going to say BC because to save space. It has beta carotene. We're going to say that this is true. I have a carrot. Carrot always contains beta carotene, so it's true. The converse is when I flip the hypothesis and the conclusion. The converse is when I flip the hypothesis and the conclusion. So if Q then P. So the converse would be if it has beta carotene, then the vegetable is a, for VG for vegetable, is a carrot. I gotta think of a vegetable that I gotta think of something that proves this true and this false. There's plenty of vegetables that have beta carotenes that's not a carrot, so I'm gonna say that this is false. I can think of something that has beta carotene that's not a carrot. It doesn't even have to be a vegetable, but I can think of vegetables that do as well. So that's false. Inverse, if not P, then not Q. So if a vegetable is not a carrot, then it does not have beta carotene. It does not have beta carotene. Again, this is also false. I could think of a vegetable that's not a carrot and still have beta carotene in it. What would that be? I don't know. I don't know my vegetables like that. All right. Then the last one is a contrapositive. If not Q, if Q not Q, then not P. So if it doesn't have beta carotene, then the vegetable is not a carrot. Again, I gotta prove the hypothesis true and still make the conclusion false. I can't think of a carrot that doesn't have beta carotene, so this is false. Can't think of a carrot that doesn't have beta carotene, so that's false. So the conditional statement P then Q and contrapositive not P then not Q, they're both true. So I'm sorry, why did I write false? They're both true. Therefore, they're equivalent statements. The converse, if Q then P, and the inverse, not P then not Q are also both false. Therefore, they are also equivalent statements. Yeah. So that's our section. Section 2.1 and 2.2. Hope you have a great rest of your day.